Let's look at another example. In this example, we're going to use curve sketching to sketch this curve using the first and second derivatives. The function is square root of 16 minus x squared. Let's sketch the curve in the way we've dealt with this so far. In this case, if I want a real number as my output, then I need to take a square root of a positive number. Therefore, as far as the domain goes, the domain is going to be any number where I can plug in x, where 16 minus x squared gives me a positive, or 0. 0 would also work underneath the square root. So that means as long as 16 minus x squared is above 0, then I'm good to go. I can add x squared to both sides. So as long as x squared is under 16 or at 16, I'm good to go. That requires my x to be between -4 and +4. So the domain is all x values between -4 and +4. Let's go and look for the critical values and critical points. In order to do that, we're going to have to take derivatives. It's going to be easier to take a derivative if I think of my original function as 16 minus x squared to the 1/2 power, or 0.5 exponent. Either way. If I think of it that way, then finding the first derivative is a matter of doing the chain rule. That means 0.5 would come out front. My inside function would be left as it is. My exponent would get reduced by 1. 0.5 minus 1 becomes -0.5. And then I would have to multiply times the derivative of the inside function. In this case, derivative of 16 minus x squared. Derivative of 16 minus x squared is -2x. And I can clean that up a little bit. That means f prime would be equal to 1x times 16 minus x squared to the -0.5 power. I'm sorry, not 1x, -1x. 16 minus x squared to the -0.5 power. -2 times 0.5 is -1. Then we have an x out front, and there you go. This can also be viewed as -1x divided by square root of 16 minus x squared. -0.5 exponent means change it to the denominator, make it a positive 0.5. 0.5 exponent is square root. So you notice that the first derivative is not defined when x is 4 or -4, because then we'd be dividing by 0. So it's undefined at x equals 4, x equals -4. But we already kind of knew we were going to get troublesome spots at the end because that was the end of my interval. If I'm looking for actual critical points or critical values, undefined obviously is one option, but that's just happening at our endpoint of our interval of our domain. But the other thing is when the first derivative is 0. The first derivative is going to be 0 when the numerator is 0, And so we get a critical value of x equals 0. If I plug that in to my function, I get a critical point at 0, 4. Now let's take a look at the second derivative. We'll look at concavity and inflection points using the second derivative. In order to calculate the second derivative, I'm going to use this version of the first derivative. This version of the first derivative requires a product rule and a chain rule to calculate it. So the product rule, meaning this is the first portion and this is the second portion. Product rule says derivative of the first portion multiplied times normal second portion plus normal first portion times derivative of the second portion. Now, derivative of the second portion is negative 0.5, 16 minus x squared to the, so that's negative 1.5. And then I'd multiply that whole thing times the derivative of the inside function, which is negative 2x. I'm going to clean this up a little bit. That means the second derivative would have been minus 1, 16 minus x squared to the negative 0.5, plus, if I take negative 1x times negative 0.5 times negative 2x, I get negative 1x squared multiplied by 16 minus x squared to the negative 1.5 power. I'm going to further clean this up a little bit so that I can reduce it and set it equal to 0 easier. So this first part is like negative 1 over 16 minus x squared to the 0.5 power. This second part is like negative 1x squared divided by 16 minus x squared to the 1.5 power. All I'm doing is utilizing negative exponents are like dividing with a positive exponent. If I want to get common denominators, then I need to multiply this by another factor of 16 minus x squared on top and on bottom. Notice that this is 16 minus x squared is raised to the first power. So when I do that, 1 plus 0.5 gives me an exponent of 1.5 when I do that. So multiply by another copy of that. Distribute this minus 1 in. What would that be? That would be minus 16 plus x squared. Notice what's going to happen here. My second derivative is going to simplify this. We're going to combine the x squared and the minus 1x squared, cancel each other out. My second derivative is simply negative 16 divided by 16 minus x squared to the 1.5 power. In terms of what's happening here, that means there's no inflection points other than, the 4 and negative 4 don't exist, but there's no points of inflection. All right, there's no way this second derivative could be 0. And the only places it does not exist are the places we already talked about, specifically at x equals 4 and x equals -4. But the first derivative didn't exist there either. So there we go. Let's talk about the concavity at this critical point. I'm going to write it down here. Concavity at 0, 4. Plug in 0 into that function, the second derivative. You would end up with a -16 over 16 to the 1.5 power, which is negative. So we're concave down. That means since 0, 4 is a critical point, 0, 4 must be a relative maximum. All right, so 0, 4 is a relative maximum. So we have one critical point. We have undefined at 4 and -4. That's where the first derivatives are undefined there. The only thing that's, the only thing that's left to do is to kind of see what happens at these endpoints. Well, if you plug in -4 into my original function, you get a 0. If you plug in +4 into the original function, you get a 0. So even though the start and end point of the interval are 4, 0, and -4, 0. So I said 4, 0, -4, 0. If you start on the left, you start with the negative. If you end on the right, you start with the positive. Or if you read it backwards, obviously you can read it backwards. Therefore, we can understand what this graph is doing. We're concave down along this entire interval because there's no point of inflection. So it always has to be concave down in between the endpoints. We know 0, 4 is a relative max. We know it's concave down, and we know the start and end value of the interval. Notice that I'm not figuring out what happens as x goes to infinity because my domain does not go to infinity here. My domain only is restricted to -4 and 4, in between -4 and 4. That's why instead of looking at going to infinity, I looked at the start and end point of our interval. Now I have graphed the critical point up here at 0, 4, and we know that's concave down, and we know that our function starts at -4, 0, it ends at +4, 0. We kind of know the shape, so we're going concave down. So it's doing something like this. 16 minus x squared. All right, something like that. Starting at -4, 0, concave down, goes through the critical point of 0, 4, still concave down, and ends at +4, 0. Let's see if I'm pretty close to being accurate. Let's graph it. Y equals square root of 16 minus x squared. Yeah, that's pretty good. That's pretty good. It looks like the top half of a circle. In fact, it is the top half of a circle. So we can see how we can graph utilizing the first and second derivatives. And by doing this, again, this gives us a really good idea about what the first and second derivatives are telling us and how the critical points and points of inflection work and all of that.